Welcome back, everyone. Okay, let's just dive right into this explainer on a seriously fascinating development in the world of local AI. We're talking about Gemma for E4B. Look, if you've ever tried to run a really capable language model on, less than stellar hardware, you absolutely know the struggle. But today, we're going to look at how this specific model is literally changing the game by packing a massive brain into a surprisingly tiny footprint. So here is what is on the agenda for today. First up, 1. The local LLM dilemma. Then we'll cover 2. The PLE architecture advantage. 3. Hardware performance benchmarks. 4. Llama-server command flags. 5. RAG tasks versus complex coding. And finally, 6. The home assistant experience. All right, let's get into section 1, the local LLM dilemma. Historically, we've had to make some pretty extreme trade-offs in this space, right? On one hand, you've got these bulky models, like the massive 35 billion parameter mixture of experts models. And yeah, they are incredibly accurate, but they demand serious hardware. We're talking way more than 8 gigabytes of memory, and you can absolutely forget about offloading them onto systems relying on integrated GPUs. It just won't work. But then on the other hand, you have the tiny sub-7 billion parameter models. Now sure, a 1.7 to 2 billion parameter model will physically fit on a weak single-board computer like a Raspberry Pi. But in practice, oh man, they can be so frustrating. When you push them to do anything complex, like say building extensions to pair with Docker sockets, they tend to hallucinate wildly, get stuck in endless loops, or just have a complete meltdown. Honestly, it's kind of been a lose-lose situation for budget hardware. Which brings us to section 2, the PLE architecture advantage. Now, the real magic here lies in a concept called Per-Layer Embeddings, or PLE for short. This is the secret sauce that fundamentally changes resource management. Think about standard models for a second. Their embedding table is usually this massive bottleneck that just eats up your system memory. But the PLE architecture does things differently. It actually grants a dedicated embedding table to every single decoder layer inside the model. So what does that mean for you? Well, it means the model can retrieve and access vastly more information at a really granular level without hogging all your precious system resources. It's brilliant because it effectively decouples memory bloat from reasoning capabilities using incredibly efficient routing. And all that efficiency brings us to a very specific and honestly very impressive number, 4.5 billion parameters. Because of this per-layer embeddings architecture, Gemma 4/E4B actually operates with effective parameters of just 4.5 billion. So it fits right into the exact same tiny footprint as those frustratingly weak models we were just talking about. But here's the kicker. Its actual knowledge capacity and its reasoning capabilities rival a conventional 8 billion parameter model. You are literally getting an 8 billion parameter brain squeezed right into a 4.5 billion parameter box. It's awesome. Moving right along to section 3, hardware performance benchmarks. Let's look at the hard numbers, starting with the ultimate test of flexibility, a Raspberry Pi 5 with 8 gigs of RAM. Now, normally, this board would struggle to even load a 5 or 6 billion parameter model. Yet, it actually runs Gemma 4E4 at around 3 tokens per second. Okay, yeah, 3 tokens per second isn't exactly blazing fast for everyday productivity, but the mere fact that it runs successfully on a single board computer is astonishing. But watch what happens when we scale up. If you move over to an older, mid-range workstation GPU, something like the GTX 1080, you are suddenly hitting a very comfortable 30 to 40 tokens per second. Let's call it an average of 35. And if you step up to an RTX 3080 Ti, it nearly triples that number, rocketing to roughly 105 tokens per second. It just scales so beautifully, going from the weakest Tinkera boards all the way up to high-end GPUs. All right, on to section 4, llama-server command flags. If you are planning to replicate this setup using the llama-server command, definitely consider this your practical cheat sheet. You really need these specific flags to unlock the model's full potential. First up is the --mmproj flag. This one is massive, guys, because it enables the model's multimodal capabilities, specifically its vision and audio processing features. That essentially turns it into an all-in-one LLM. Next, you've got --jinja, which is absolutely crucial for advanced templating and prompt formatting. And finally, the webui-mcp-proxy flag. This is the one that allows the model to hook into external tools, like a Docker Model Context Protocol, or MCP, server. It basically gives the model hands to actually interact with your system. Let's pivot to section 5, RAG tasks versus complex coding. So, how does it actually perform? Well, the victories here in retrieval augmented generation, or RAG, are absolutely fantastic. When you pair this model with self-hosted, free and open source tools, it becomes a total powerhouse. It does a brilliantly fast job of summarizing PDFs directly from the llama-server web interface, plucking out exactly the relevant details you need. It seamlessly processes queries through note-taking apps like OpenNotebook and Blinko, filtering out all the unnecessary fluff. And honestly, it is highly effective at scanning through massive, dense server logs to hunt down buggy code, and it even automatically generates really accurate tags for document management containers like Keep and Paperless AI. When it comes to organization and summarization, it seriously punches way above its weight class. But, okay, we do have to be realistic here. We can't ignore the limitations. It is still just a 4.5 billion parameter model, and complex coding tasks are exactly where the illusion breaks down. While it could easily check in on existing Docker environments, when the author asked it to actually spin up new, fully functional containers via that Docker MCP server, it completely failed to call the right creation tools. That's something larger 35 billion parameter models can do in their sleep. Furthermore, if you ask it to write complete Ansible playbooks for automation, yet you are going to get malformed code packed with multiple errors. It simply doesn't possess the deep reasoning required for complex, multi-step code generation. Which brings us to our final topic, Section 6, the Home Assistant Experience. So the author tried hooking Gemma's E4B up as a conversation agent for Home Assistant server. And the results, well, they weren't terrible, but they definitely highlighted its boundaries. The model really struggles if you give it vague commands. It frequently fails to select the correct smart device in the house. And, very similar to the Ansible playbooks issue, it just lacks the logical depth for complex chains. If you try to have it create automations with multiple if this, then that conditions, it gets totally tangled up and messes the logic up entirely. So it's okay for basic toggles like turning a light on or off, but it is definitely not ready to be your fully autonomous smart home architect. Which leaves us with this final thought. Despite its limitations when it comes to heavy coding or complex automations, Gemma 4 E4B's ability to run locally, securely, and efficiently on almost anything really is a game changer for daily productivity and RAG tasks. In fact, based on all this testing, the original author is actually planning to use some LXC container pass-through wizardry to turn an old, dust-gathering GTX 1060 laptop into a dedicated Proxmox workstation, specifically just to host this model. So, I have to ask you, what aging hardware do you have sitting in a closet right now? And is it time to bring it back to life with a tiny, brilliant local LLM? Thanks so much for joining me for this explainer. Keep tinkering, and I'll catch you in the next one.